Okay. So I can unfreeze it there. So on what coordinate over here do you think do you want to start with? Which one do you want to do first? Let's try R first. Absolutely, that's fine. So for R right here, it's going to be, what is its distance from the origin? Its distance from the origin is 5. What's the angle measure? Anybody have it? Raise your hand and tell me. Anybody? Hands? What's degrees? Let's stay in radians unless I explicitly say degrees. Okay, always stay in radians unless I explicitly say degrees. What do you think the degree measure is, Yana? It's pi. Why is it pi? Yeah, it is the same place. I like that. The same place where pi is. You go from the positive x-axis to the ray created by the point being connected to the origin. So that is pi. So that is 5 pi. Absolutely. Absolutely. That's great. Yes?
Is there a way to mark if you use a Cartesian or a polar?
No, you just have to context. Yes, absolutely. Yes, there's no symbol if that's what you're like. There's no difference in brackets. That's a really good question actually, but no, there isn't. What's another quote easy one to do up here? What's another easier quote? I mean, easy is a bad word to use. What another one? What's one that's similar to R? V. So that would be 5 comma what? 3 pi over 2. And what's Q? 5 comma 0. Or 5 comma 2 pi, or 5 comma 4 pi, right? You can go around as many times as you want, but that's 5, 0. So are there points where they have the same Cartesian and polar representation? Yeah, it is possible. So you could write this as 5 comma 2 pi. It is possible. That is possible. Okay, so what about U and P? What's slightly different about U and P? What's a little bit different about U and P? The distance. So between the two, the distance and angle are both different. That is correct. But if you were going to compare R, Q, and V to U and P, what's the primary difference between those 2 points and the other 3? What's the primary difference? They're not on an axis, right? So first of all, what's the distance? Let's just assume that's 4 and that's 3. What's the distance for U? Oh, it is still 5, right? Correct? What's the angle measure, though? And you don't have to give it to me in exact form. You can leave a trig function in there.
37.
Again, be exact. Leave a trig function in there. Rounding is not something you'll get credit for, generally speaking, on the AP exam, so let's not round here. Give me the exact angle measure. The exact angle measure. Exact. Tan inverse of 4 over 3. Yes. Correct. Stop there. That's fine for now. What about P? Who wants to tell me what the polar coordinate is for P? Yeah. It's not exact, it's not exact, it's not exact. It's 57.5, whatever, right? Do tan inverse 4 over 3 and you'll see it's not exact. So yes, it's about 60, but we need to be exact here. What about P? Assuming that that's 6 and 3, what's it going to be? The square root of what? What's the distance? Look at 4. So it's the square root of what? 36 plus 16 is? 36 plus 16 is? 52. So it's the square root of 52 comma tan inverse of what? Of what? 6 over 4, so 3 over 2. And I'll leave it as 6 over 4 just so you can decode this a little bit more smoothly later. So could you use your calculator to get those exact angle measures in radians or degrees? Absolutely. But for now, we just want to know where they come from. How are we feeling about these? 5 is you're totally down with this. 0 is you have no idea what your name is. Where are we? Everybody votes. Everybody has to vote here. What do you think? Kay, prove that you're paying attention by voting right now, please. Hi.
Wait,
Then another way to do it is, hey, what kind of graph paper is this? This is polar graph paper right here. This is polar graph paper. So we had Cartesian points in Cartesian land converting to polar. We could have points in polar going to Cartesian. So this point right here, what is that point in polar right there? P. What is that point in polar? What point is this right here? What's the distance from the origin? What's the distance P is from the origin? Nope. It is 3. And what's the angle measure? Pi over 4. It's literally right there. So it's 3 because it's 1, 2, 3 away from the origin, and it sweeps out. It tells you right there. It's on the pi over 4 right there. So now we need to figure out what the Cartesian is. So this is the polar coordinate. Now we need the Cartesian. Do we have simple formulas to figure out what the x and y coordinates are? Okay, you figured them out before. X was equal to what? R
times sine.
Cosine theta. You got to get this right. Careful, 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 careful. Y is equal to R sine theta. Do we have both of those values?
Yeah.
Therefore, what does x equal? 3 cosine, and y is equal to And in this case, sine and cosine of pi over 4 are both the same thing, right? So what do we have for our coordinates here? 3 root 2 over and 3 root 2 over 2. So this coordinate right here, that's in polar. If we wanted to go to Cartesian, it would be 3 root 2 over 2, comma, 3 root 2 over 2. So if you have r and theta, you can go directly into Cartesian coordinates. Absolutely, directly. Okay, so this is where, so the question I always had, these are equivalent structures. R equals 1 is a unit circle, and, right. Okay, so that's relatively straightforward, and you know how much I loathe using the word straightforward or clearly, but it's relatively, we already believe in this, we have a relationship, it falls together really nicely. Here's where it gets a little bit more fun. Write the equation y equals 1 using polar coordinates. Try that yourself. Write the equation for y equals 1, for a horizontal line of y equals 1, using polar coordinates. So we have this equation, this is a Cartesian. So basically you're writing a relationship between r and theta. What relationship is there between r and theta that gives you a horizontal line at y equals 1? What would that one? I don't want the answer. How do we start this one?
I change x and y to r cosine theta.
But remember, which x and y? Oh, in here? Ah, you could. You could, absolutely, if you want. Really, actually, let's see what happens here. So you did, I really like this. So you did, in the red circle part?
R equals to.
Okay, so you have r is equal to this right here.
X squared plus y squared.
And you plugged in r cosine theta and r sine theta. You could do that, but it's going to end up with r equals r.
Yeah.
Yeah, right? So which is true. So here's the thing. What are the relationships you know? If you ever get lost in polar land, what relationships do you know? Yana? Yeah.
Now y is r sine.
Oh, y is equal to r sine theta, right?
And y is
What do we want y to always be?
1.
Exactly. 1 equals r sine theta, right? So what does r equal? 1 over sine theta. Done. It will frequently be the case that you will spin your wheels looking at a polar question, going, I don't know, and then it'll be like, done. Like, just because it's hard to find doesn't mean it's long. Does that make sense, everybody? So this is a relationship, we know y is always equal to r sine theta, but what does y always equal if we're graphing y equals 1? It always equals 1. So therefore, we have our relationship r equals 1 over sine theta. Done. That's it. Yeah, and you can draw it at point, so we have r equals 2 sine 2 pi over 12, like this. So what's that going to be? R equals 2 sine of pi over what? What is sine of pi over 6? You need to know this. What is sine of pi over 6? A half, yeah. So that's going to be what? 1. So is my angle measure a little off there? Well, actually, no, it's not. My angle measure is not off much at all, actually. R equals 1. So what is, so R equals 1. So is this distance roughly 1 from there? It's roughly, like that's 2 right there, right? Where's 1? It's right about there. My estimation of 15 degrees is a little off. So did we just confirm it goes this way? So this first pedal is going to go around like this. You are going to have to do 2 big things with polar graphing. You're going to have to calculate arc length, which is really straightforward actually. And you're going to have to find out the areas of these pedals. But to find the area of the pedal, you need to use a definite integral. What's the difference between a definite integral and an indefinite integral? You need a limit of integration, right? So here's the challenge. In order to do these integrals, the integrals themselves are really easy to do. What's the hard part to find out? The starting and the end point. Because if you start and end it wrong, you will get the wrong answer. So they'll ask something like, what's the area of this pedal? You need to know where do you start and where do you end, because you can make 2 big mistakes. You can either pick something that runs from like here to here and you only get part of the pedal, or you do too much. So for example, we know it starts at 0 and it goes around like this. When does it get back? What's the angle measure when it gets back? It's sweeping this out. So that's pi over 12. There. This is pi over 4. Keeps going, keeps going, keeps going. When does it get back? Right there again. Pi over what? It's going to be pi over 2. So the first pedal happens from r equals, so from theta equals 0 to theta equals pi over 2. Now the really fun part begins. I could ask you, which pedal does it go on next? Which pedal is next, do you think? Well, what could we plug in? like we go to like a little bit. What's another pi over 2 is right here. We could do pi over or 3. Like what? Pi over 1.5. We could run that and find out where it goes. Does it go down? Does it go down? What do you think? Let's do. This is important. Let's do this actually because it's really. We have a sector. A sector was 1/2 what? R squared theta. Correct? Is everybody with me right there? Okay. So if we wanted to find the area of that limacon, what does R equal? What does R equal? 3 plus what? 3 plus 2 cosine theta. So where am I going to plug that in? For R. So what do I end up with? I end up with 1/2 3 plus 2 cosine theta. Now here's another thing here. What is our theta going to be? How much? Instead, it's not theta. What is it going to be? An infinitesimally small slice would be what? Delta theta, d theta. D theta means an infinitesimally small, so this turns into d theta right there. And what are we doing? We're integrating. And remember what did I tell you before? We need to know all about orientation because we want to know where we start and where we begin. Where do you think we start on this one? Well, let's start at 0. Theoretically, we could start anywhere we wanted, really, because they go in circles. What is one cycle for this thing, do you think? What does it look like one cycle is?
There's 2 of them.
So does it go around twice in 2 pi? Or does it go around? So I'm asking, is it 0 to 2 pi or is it 0 to pi?
0 to pi times 2.
Oh, so you want to double. So you could go halfway and double it. That's fine. Noticing symmetry is really important. Let's go all the way around first, okay? Does everybody understand what KU said right there? We could go halfway and double it. Let's go all the way around because I want you to realize what that is. So it starts, let's go here. What's cosine of 0?
1.
Cosine of 0 is 1. That looks like it could be 5 because it's further out, right? And then it's going to go all the way around. When does it get back to there? What's the period on cosine?
2 pi.
2 pi. Does this make sense, everybody? So we should integrate from what to what right here? 0 to 2 pi. So one thing that's really important for this one be, it would be the integral from what to what. And there's a really nice hint there. What is it the integral from and to?
0.
0 to what? Pi over 2 of 1/2 what? 2 theta squared d theta. Exactly. Right there. And if they'll be really tricky. They're going to ask you something like, what's the area of all the petals? So then when you multiply this by 4, right? You could actually do this in symmetry. You could go from 0 not to pi over 2. You could go 0 to what? Pi over 4. There's a symmetry right here, isn't there? So you go from 0 to pi over 4 and times 2 if you wanted just a petal, times 8 if you wanted all of them. Be really careful about this. It's not generally the calculus that trips people up. It's the what's the angle measure, where am I starting and where am I ending up. That is the trick.